Hello everybody, I'm back again to talk about more integrated rate laws. This time we're going to do with second order integrated rate laws. We're dealing with the case again of the chemical species A going to products where it's second order. And it's going to be second order in the form of rate is equal, I'm using R for rate constant times A squared. I'm not going to consider the case of rate is equal to constant A times B. That's another second order type. I call that type 2. It has a known solution. It's actually quite doable. It's just we have to draw the line somewhere. So if you are interested, email me. I have a whole set of notes that include that and more complicated cases that I teach in other courses that are more advanced. It's not significantly a big breach in terms of learning. You just want to keep it concise because we have a lot of stuff to cover in this course. And so we're going to focus on this case right here where it's A squared. And so a lot of times it's called second order type 1. And so let's just talk about the units. So if we have rate, it's going to be molarity per unit time. Let's just put it in seconds for the sake of argument. This will be molarity squared because it's concentration squared. That means that K has to be 1 over molarity times seconds, both in the denominator. That can also be expressed as molarity inverse, seconds inverse. Be familiar with that. A lot of times students that throws them, and make sure you understand that the reason I'm just looking at this saying that this is what the rate constant units are is I'm making sure the units on the left equal the units on the right. I mean, you do not have to memorize this. You should try to understand it. Again, if you know calculus, this would involve different. This is going to be this rate is equal to K A squared is going to be equal to the change in A, change in T. If you do know calculus, you can refer to my note sets, and this is going to be a polynomial type of integration. It's actually not hard at all. And if you don't, that's fine. It's when you learn calculus, you'll be able to do a problem solve something like this easily. The solution to this equation, if I want to write it in a convenient form of a straight line, there's different ways I can write it. That's a good way of expressing it. This equation here, I have a denominator, concentration at a certain point in time. It's a function of time. Here it's in the denominator is initial concentration. I'm using the 0 symbol for initial times 0. And here's KT, the rate constant times time. You can think of this in the form of Y. Here's B, the intercept, and here's MX. So the way you would plot this linearly is 1 over AT. And here's time. It could be seconds, minute, hours, what have you. Now, the last two equations that we looked at, the 0th order and the first order, both went down. This one, the slope's going to go up. So that's it's a little different looking. Straight line. It's a linear form. So this is the one of the solution types. It's in a straight line. There's little ways we can write this out. You can rearrange it. It's good to know. So that's how the plot looks. The units will have inverse concentration, typically molarity, inverse time, often seconds, inverse seconds, but it doesn't have to be. Let's do the half-life. This is going to suffer from a similar problem that the half-life did with the 0th order, namely that if you do successive half-lives for a problem, let's say you're going from 1 molar to a quarter of a molar, solution, that would be 2 half-lives, that you cannot use the same concentration from the first step on the second step. So we'll do a calculation where we can do it 2 ways. And again, just like the 0th order, I think for successive halvings, just using the integrated rate law directly is the easiest way to go. But I like to show it 2 ways so you can decide for yourself. So first, let's derive an equation for the half-life. So we have this form here. For when you're at the half-life, A sub t will be 1/2 A naught. So that will put the 2 up in the numerator to give you this. And I'll denote K, the half-life T as T 1/2. You can pull this over to one side and then isolate T 1/2, and you end up with a formula T1/2 is equal to 1K, the rate constant over A naught. So the big thing to notice, unlike the 0th order, A is in the denominator in this time. So as what happens is as you go through successive half-lives, this drops, and the half-life of each step actually gets longer, not shorter, like with the 0th order. And again, to refer back to the 1st order case, there's concentration dependency in the 2nd order half-life, just like the 0th. Recall that for the 1st order, there is no concentration dependence. So that's where the half-life, including for successive calculations, is very convenient. So let's do some calculations. So I forgot my eraser here. Let me see what I got in my pocket. I got a piece of paper here. I should have bought an eraser when I bought this board. I didn't, and I'm just using napkins. So sometimes when I teach at school, I find that the erasers are kind of soppy, and I use a napkin anyway. I don't know what's going on with the erasers, but at any rate, let's do a problem. We'll say we have K in this problem is 0.100 inverse molarity inverse seconds. Just seeing that should tell you that it's 2nd order. It should tell you it's 2nd order because of the units. I will not necessarily say that on the exam, that it's 2nd order. Let's do a problem where we're going from 1 molar to 0.250 molar. Now you could think of that as 2 successive half-life approximations. I'm going to first do it the direct way. I'm going to rearrange this equation. 1 over AT is equal to 1 over A naught plus KT. Rearrange that in the form we have time. So we want to know how long does that take. Equals 1 over K, 1 over AT minus 1 over A naught. So A sub 0, or A sub naught, call it that's really a 0. And so we have here, we have what K is. I'm just going to write there, if this is in the, these are inverted, it's in the denominator now, they'll come up to the numerator. Then we have a time T, 1 over 0.250 molar. And that's going to, you're going to subtract off 1 over, just 1 really, 1 molar. So you can see the molarities cancel. You're left with just seconds, and this number comes out to be 30 seconds. 30 seconds, check it for yourself. Let's do this by successive half-lives. I think the way I did it initially is easier. So let's go from 1 to 5. So we'll call that T 1/2. So we're going from the 1 molar to a 0.5 molar solution. Let's do that out. So that would look like, using our half-life formula of T 1/2 is equal to 1 over K times A naught, A sub 0. This would be 1 over, well, I'll put the molarity in seconds in the numerator, because denominator over denominator, 0.100, and then we're going to have times what? 1 over 1.00 molar, which does not affect the number, but we should write it in to get our units correct. And so this gives 10 seconds. So to go from 1 molar to a half of a molar solution took 10 seconds. Hopefully, unless I made a mistake, the second half-life, to go from a half a molar to a quarter of a molar, should take 20 seconds. So now here's the key step where people would make a mistake, is you want to maybe put in 1 molar. You don't. Put in 0.500. They change. This has a dependency on concentration on each step, and this ends up being 20 seconds. So the total time is the sum of these. That's going to be 30 seconds. Analogous to the problem with the 0th order, except here the half-lives are getting longer, and in the prior case they were getting shorter. And with the case of the 1st order, there is no change, they're equal. So you can see which way you like is better. I personally would just use an integrated rate law directly. So let's do another problem, real simple. Let's say we have some number that has nothing to do with the half-life. What's the concentration of A at 17 seconds? And the reaction, again, we're starting off with a 1 molar solution in A. So what's it after 17 seconds? Clearly not the half-life or anything like it. So let's just do it out. You can do this a couple ways. You can rearrange this equation, if you like, to be A sub t is equal to A naught 1 plus A naught kt. Rearrange this, pull, let's see here, make this into the form of a common denominator and then invert it, and you'll get that. It's really simple. Do it on your own. And so let's do it out. We have A at time 0 was 1 molar, 1 plus 1.00 molar times K, 0.100 molarity times, oh, that's wrong, inverse molarity, inverse seconds, and then we have 17 seconds. So the time units cancel. What else do we have here? We have the molarities cancel. So we end up with dimensionless in the bottom and molarity in the top, and it ends up being 0.370 molar. Verify that for yourself. If you don't like doing it that way, you can plug it in here. And that will be equal to 2.70 inverse molar, because again the seconds cancel. This is inverse molarity, and here the molarity is in the denominator. And when you take the inverse of that, if that's 1 over A sub t, take the inverse of it, 1 divided by 2.70, and that will give you A sub t is 0.370 with units of molarity. So you can do it either way. I like to give you different ways of doing these problems. Don't have to copy me. You can do the algebra your own ways. Just don't make something up at random. There are ways of doing these problems correctly. I certainly will provide formula sheet with the basic information. I usually provide a formula sheet that's sufficient to do the whole exam. And so you can look at that ahead of time, and you'll have all the equations there. What else was I going to say? So tomorrow and the next day beyond that, we'll be finishing up kinetics with the videos, and I'm going to keep putting them up as I make them. For those of you, there's about 6 or 7 people now watching. That's great. We'll get into Arrhenius behavior. We'll talk about mechanisms. We'll talk about catalysts. So we'll get to be, some will be quite qualitative at this point, but definitely if you're working ahead, or if you're in semester watching this, because I realize people will be watching this later, be working the skill builders, be working the problems in the note sets. I'll have solutions for them up, but work them anyway on your own. If you need more problems, I'll put problems in the book up, although I don't really use the book in this course. I make my own material up from experience and a million books I have laying around, but certainly I can recommend problems from a book as well. But I think most people, for the 100 problems I put up for every chapter, will have plenty of problems to work. So on that note, I'm out of here. If you heard any noise in the background, it's my friendly raccoons hanging outside. They're doing something, I'm not sure what, but at any rate, it's nighttime here in New York. Have a great night or a great day when you're watching this, and I'll catch you later. Take care.